Yeah, hello everyone. My name is Alex Serban. Thank you for the invitation. It's actually a great pleasure to be here and talk to such an active community. For the past years, I've been a PhD student at Radboud University in the Netherlands, and I also got the chance to visit a few other universities in the Netherlands and outside, from which some of the things that I'm going to talk about are developed within Leiden University and together with a company called the Software Improvement Group. So some of my research topics and research interests in general are around machine learning robustness. And as you already know, robustness has multiple facets or can be defined in multiple ways. The way I look at it is from a micro perspective, sort of an algorithmic robustness perspective. Either our algorithms are, for example, maintain training performance when we test them against new or noisy samples, especially noisy samples. And also from a macro perspective or a system-wide perspective, where this means that the system where we embed these components has the ability to cope with errors or some erroneous inputs. So you can think about the way we provide redundancy to some of the components or the way we take the final decisions. And also we mentioned that, in machine learning, the boundaries between robustness and trustworthiness and all these concerns about, for example, fairness, privacy or transparency, they are not so transparent to us. So these boundaries they erode, and robustness can sometimes also be defined as fairness or has some implications to transparency. So one of why this is we should look at the robustness from these perspectives. First of all, there is no completely robust algorithm. So we don't have a completely robust machine learning algorithm to use for our data. And so we have to look at the whole system to also alleviate some of the algorithmic weaknesses. If we think about redundancy or if we think about using machine learning in more high-stake decisions, then we need to also think about the system. But also, if we need high uptime or all these concerns that you're probably facing as practitioners, then you know that we also have to take into consideration the system. So some of the examples, of robustness in the wild are the typical adversarial examples where we add some noise to an image and then it gets classified as a completely different into a completely different class than the intended one. Some of the most common, racial bias that can be found in algorithms that are already deployed by big companies such as Microsoft or Amazon. But one example that it's actually I like a lot is that robustness, if we look at top 50 keywords in submissions to ICLR or other machine learning conferences, we see that robustness is always in top 5. So this is the community also in research is actually starting to pick up this topic and to consider it valuable. Also inside the EU, so we were talking about having a meetup in Amsterdam. Inside the EU, there is a high-level expert group on AI set up by the European Commission, and they published in 2019 already some guidelines for developing trustworthy artificial intelligence. And in these guidelines, they have 3 main pillars, and these pillars are lawful, ethical, and robust. So one of their main topics for example, technical solutions refers to robustness. So this type of concerns will be also translated to policy in the future and actual laws, and they're becoming a bit more important. So why am I telling you this? In general, because good engineering is a prerequisite for building robust machine learning systems. So we talked about this algorithmic and system perspective of robustness, and we started to look at engineering as a solution to provide system robustness. And we started to look at engineering practices, the topic of today's talk, as a prerequisite, as what do we have to do before actually even thinking about robustness. So which are the basic engineering best practices that people should use in their machine learning projects. So some of the questions that I will try to answer today and give you a bit of a hint towards the solutions are, for example, which are the software engineering best practices for machine learning in general, but also how are the more traditional software engineering practices impacted by the use of machine learning components. Which are the new practices being proposed, or how do the old ones are modified, and to what extent these practices are actually adopted by practitioners. So what we're interested in is not only that a bunch of people put up some practices up there, but also do practitioners adopt them? And if there is, which are the effects of these practices, and what do practitioners think in the end about these practices? Are they valuable or not? So some of the research that we're doing is guided by a process that we define. And the way we investigate these machine learning engineering best practices is that we start by reviewing the literature. And in the literature review, we have quite of a thorough process, but in the end, we review both academic, so research papers and workshop articles, but also what we call gray literature, blog articles, or maybe YouTube videos from different conferences that propose new ways of developing engineering machine learning solutions. We actually review them and we publish what we consider the best results on GitHub in what's called an awesome reading list. Ours is called the Awesome Software Engineering for Machine Learning reading list, and I invite you to check it out. After this, we actually try to standardize the way we look at these practices and embed them in a practice catalog. And then we try to measure their adoption and their effects. And we do this by using a survey. I'm going to talk about this a bit later, but also by interviewing practitioners. So for us, it's very important that we have a wide pool of data and teams of developing these systems, but also that we get insights into in-depth discussions with practitioners to understand some of the results from the survey and generalize a bit better. And then we restart this process for different concerns. So we did it once, and this is the paper that was mentioned at the beginning for more general engineering practices for machine learning. And then we started to add concerns such as trustworthiness, for example, what I talked in the beginning, robustness or fairness, and so on. So which are the more engineering aspects of these problems? And then we looked at, for example, AutoML. It would be very nice for us if we can automate the adoption of some of these practices, or in general, some of the steps in the development process. And then, we also looked at more architecture level. How do we embed these components in systems? Which type of decisions linked to which quality attributes and so on? I think there is a question. Or?
Yeah, I just wanted to mention, because I read it in the paper and I didn't realize what it was beforehand, but the gray literature, what that is.
Yeah, so that is typically blog articles or white papers published by companies, but also different, for example, YouTube videos that we parsed from different talks. So this is generally, we call it gray literature, and it's called like this because it's not peer reviewed. So it's not set up in an academic context. Yeah, so as I said, today I'm going to talk about the first part, and I'm going to touch a bit on the trustworthiness part. But here I just want to give you a hint about this practice catalog and some of the results of the survey. So at the beginning, we started this process by looking at general engineering best practices for machine learning. So after the literature review, what we ended up is with 29 practices, which later have grown to 45, including trustworthiness. And then we did a bit of we tried to group them into different categories and to describe them. So what we ended up with by looking at different, for example, machine learning development processes, I guess you're familiar with, for example, CRISP-DM or this Microsoft process for machine learning. We ended up with a process with grouping into 6 categories. And these are starting from data, training, coding, which for us means that actually the machine learning model gets embedded in some sort of application, and then deployment, which is more the operations part, but also more traditional concerns like how do we form a team? So we have machine learning experts, and now we have to embed them in a team of also engineers. So how do we communicate, how we take decisions, and so on. And overall, because the impact of machine learning, if it's improperly used, can be very big. Also, we look at governance. How do we establish values? How do we, for example, assess risks or ensure transparency? And to describe these practices, we saw some inspiration from design patterns, which is a language that developers and engineers typically speak. And we decided on using intent, motivation, applicability, and description, which is more or less what design patterns offer in general, but also publish some of the results and make them available from our survey. And the practices are also, they have in the catalog some indication of difficulties or how hard it is to apply them. To give you Also, a different look at this type of process. That the groups that we ended up with are, typically you collect some data, you clean it, you label it, and then you run your training experiments. And afterwards, the machine learning model gets tested, but also built in some sort of pipeline, and then deployed and monitored and so on. So this is one of the core process that happens for machine learning. And at all these stages of the process, we also have sort of governance and teams. So you can imagine that for training, we have in the team, we have machine learning engineers or developers or scientists. But for deployment, we actually have MLOps people or just operations people. So you can look at our grouping also as a process. So just to give you an example, one of the practices, and this is the first one, it's using sanity checks for all external data. And as you can see in the catalog, the intent is to avoid invalid or incomplete data being processed. And then we follow this design pattern type of description with, you should apply this to any machine learning algorithm. Some of the practices actually applied, we identify them only for some types of machine learning algorithms. For example, if you're only using some sort of personal data or identifiable data to users and so on. And then you have here the category and you have the difficulty. And I'm gonna point you towards the website, and you can play with it and you can see sort of how the practices rank and how they relate. So as I said, this was the first step, to classify, to sort of identify and classify and describe the best practices. And what we did afterwards, we tried to measure the practice adoption and get some data from practitioners about these practices. So in one of the steps for measuring the practice adoption, what we did is that we ran a survey where the intended audience were teams building software that incorporates sort of machine learning components. And in the survey, we had three types of questions. The first one were more general questions regarding the team size, the team experience, and some more background, for example, the type of data used in the projects and so on. Then after that, we asked them about the practice adoption. And for the practice adoption, to make things a bit more easier, we had a scale with 4 types of answers. Starting with not at all, that the practice is not, is not adopted at all, and ended up with completely, which means that everything was adopted in a project. And the last step where we had some effects. So these effects, for example, were meant to test hypotheses, and I'm going to talk about this a bit later. Either applying a set of practices or any grouping of practices would lead to an intended effect. So just as an example, one of the effects were that teams were able to easily and precisely reproduce past behavior of the models and applications. So this is, for example, reproducibility, or, we had other effects that I'm going to talk about. And in this survey, we actually collected until now, I think now we have in the benchmark about 550 complete answers. So these are answers that we can use to generalize, and they're coming from teams all over the globe. So we have over 500 teams of practitioners that took the survey. And this is over the time span of 1 year. And we also publish a report that I'm going to point you towards. Every year, we try to publish a report in the spirit of, if you know, the Stack Overflow survey. So some of the results that we obtained from the survey, for example, just to give you some insights, one of them is that tech companies, as you would expect, they lead in practice adoption. And here, what we have in the picture on the right, we have the percentages of answers, types of answers, and then they are grouped by the organization type. And we can see that in general, the completely and mostly give you a very fast impression of practice adoption with a bit of more complex algorithm that I'm going to describe to measure the complete adoption. But here you can see that if you only judge the completely type of adoption for each practice, you can see that tech companies are leading. They're followed by non-tech companies, as you would expect. And for us, non-tech companies are types of organizations like banks or large enterprises that have processes outside tech. Tech companies are, for example, semiconductors, social media companies, and so on. And we can also see that the research organizations, of course, they have the lowest practice adoption, but mainly for the deployment practices, because in research, no one really deploys and runs in production machine learning models. Some other insights that we can share, for example, that practice adoption increases with team size and experience, which is, larger teams, they have more members and they tend to adopt more practices. You might think that, of course, this is logical, but this is data coming out of, the survey results. So it's another confirmation that for the survey. And also more experienced teams, they tend to adopt more practices with a small hiccup. If we look at teams with more than 5 years of experience, we saw that actually their adoption rates drop. And we ran this 2 years in a row, and we saw that 2 years in a row, more experienced teams, they tend to adopt less practices. We hypothesize that this is the result of the fact that, they are not aware yet of all the practices because or maybe they think that they can do better.
Wait, did I hear that correctly? That more experienced teams adopt more practices. Okay, not less practices. Yeah. Okay.
No. Less practice is only the ones that are more than 5 years of experience.
Okay. Oh,
so here the trend is sort of increasing towards more adoption, but teams that have more than 5 years of experience, they also tend to adopt less practices.
And that kind of goes in with the saying, you can't teach an old dog new tricks.
Exactly. Yes, I think so. All right. So we also divided these practices by something we call the type of practice. And we have 3 types of practices. These are traditional software engineering best practices, such as, for example, running regression tests on your code. Modified practices, which are derived from traditional practices, such as testing, for example. They are modified for machine learning, such as testing for bias instead of testing for different inputs, and completely new practices. And what we observed is that machine learning engineers in general, they tend to adopt more the ML specific practices, which for us, it kind of means that machine learning teams are still formed mainly of machine learning trained people rather than traditional software engineering. And this, as I said, we ran the survey 2 years in a row, and then these results, they preserved over time. Also, with the prerequisites, we can split the data using the data type used. And we have here for tabular text, images, and videos, they are more or less equally distributed. And we have graphs and time series, which are less distributed. That's why graphs is not even included. But what we see is that the adoption of practices is largely independent of the data type used. This is something that, of course, we expect, because engineering in general should not be necessarily linked to the data type used. But also, if you think about images and videos, then the way the data is collected and stored is a bit different. So that's why there are small differences each and there. So if we go now back to our example practice, we talked about how we measured this adoption, that we have this scale on the survey, and we have over 500 answers. Now in the catalog, we also added the adoption rate. So for each practice, once you go online and check the catalog, you'll see that for each practice, you can see the adoption by team experience, by team size, by data type, or by organization type. So in case, for example, you're a startup and you don't really know kind of how to guide your development process, you can actually see straight away how you compare with other teams, at least in our benchmark. And also there are a few other sections where you can see how practices are linked and related, but also you can go and read where these practices come from yourself. And, if you have any recommendations, we welcome you to make any changes. So here we have a list of 29 engineering best practices that we identified at the beginning, and they are here ranked by the most adopted to the least adopted. And I'm not going to go into the details of the ranking algorithm. We use some sort of a way of removing noise that's coming from answers that are in between them. When you cannot say completely, you have to say partially, and so on. So as we can see, the top most adopted practices are actually related to training, which we expect, as this is the core part of machine learning. And some of the least adopted practices are actually related to coding, deployment, also training, but these are more complex ones. So just to give you an example of some of these practices, we have the top most adopted practices. The first one is actually capturing the training objective in a metric that is easy to measure and understand. You might think this is trivial, right? You can have accuracy, but actually, as you know, in business context, these metrics have to be defined also in terms of business benefit. And then sharing these clearly defined training objectives within the teams, discussing that we have to improve. For example, I'm just giving an example of revenue. This might not be directly linked to a machine learning metric. So it's actually nice that these type of practices are widely adopted and people try to communicate them. Also, for example, writing reusable scripts for data cleaning and merging, something that, you in research, when you just do some work, maybe in a notebook or so, you don't really do. Well, now some example of the least adopted practices. The least adopted practice is actually assigning an owner to each feature and document its rationale. If, in this case, we filter out applications that use deep learning, for example, and they select their own features and so on. So it's a bit sad to see that people use some features that work, but then they don't document them at all, or they don't remove or archive the features that are not used, in applications where they use algorithms that use features. But also, for example, that shadow deployment, which I think is closer to the MLOps community. This means that, you deploy a model in parallel and then you don't put it straight in production, but you actually observe it a bit. This is one of the practices that is within the least adopted ones. So there's plenty of room for improvement, I think. Now jumping to the effects, as I said in the,
Yeah, just on that last slide, sorry to kill the momentum, but
no.
I was wondering on the shadow deployment, because that is something that has come up quite a bit in the community. Do you have any theories on why that is so low adoption?
Yes. So as I said earlier, we also talk a lot with practitioners and we interview them and we try to find out if these findings are actually real. And what we found out about shadow deployment in general is that, many practitioners are still struggling with either developing or adopting some tools that can do this automatically. So they don't want to, they just want to, we use a tool that can do shadow deployment and then they use it. But until they select the best one, or we had practitioners that actually develop their own tooling, this takes time.
Oh, interesting. So it's a lack of tooling then in that case.
Yes, for them, I think it's a lack also of tooling, but also of tooling adoption.
Yeah.
So for people that use, for example, SageMaker or some, H2O.ai, then they use it because it's embedded in the tool that they use in the tool chain.
Yeah, that's amazing. Cool.
Yeah. So now, as I said at the end, we had these effects, and I'm gonna talk here about 4 of the effects which were in the original paper. Meanwhile, we updated the survey and we have a bit more effects. So at the beginning, we had the 4 effects. They were agility. The team can quickly experiment. It's very agile. They can deploy. They can roll back, and they can do this very fast. Quality, which is the software itself, should be of high quality, well tested. Use some static analysis tools, don't have huge methods, and so on. The team is effective, the way the experts with different skills they interact between each other, and we also have traceability, which is more that the outcomes of the production models can be traced back to model configuration. And we used some groups of practices to do some statistical analysis. And we saw that actually from some groups of practices, we have a linear relationship within groups of practices and this effect. So this means that, we can deduce the effects from the practices. We also trained some classifier to see if there are nonlinear relationships between the effects and the practices. And we found very strong relationships, and we can predict, for example, the effects from the practices. And with this classifier, we use the importance of each practices to the effect to actually try to understand, and suggest which is the best practice to adopt for achieving one of the effects. So Just to give you an example of these practices, the top 3 for all of them, for agility, for example, automating model deployment. This will give you, a lot of agility, but also, for example, having parallel training experiments. If you can enable this, then you can actually play a lot and you can run experiments very fast and you can be more agile. Similarly, for example, for software quality, just using continuous integration or having automated regression tests will improve your software quality. So these are not all of it, these are just the top 3. So just to give you an example about how this importance, here in the plot on the right, we see the practice importance, which these are the Shapley values, and these are plotted against the practice adoption, which in this case should give you an indication of difficulty. If you think about one practice being highly adopted, then it should also be a bit easier to adopt. So some of these plots might seem confusing now because of the numbers, but this type of analysis, if you will go on the website, you'll see that, you will understand, if you want your team to be a bit more agile, you will understand which practice to apply and which is the most, you can do some trade-off analysis for yourself and understand if it's worth to invest the effort to, use a practice that is least adopted or more difficult to achieve some of the effects that you want or not. So this will give you some sort of, you can understand where you are and where you want to go and maybe guide you a bit on this path. So I hope by now I answered some of these questions that I posted at the beginning, sort of, what are the effects of this practice adoption and can we predict them? But for us, this, this is the paper that I was mentioned in the channel, but for us, this opened more questions. So one of the questions that we tackled is how about trustworthiness? Now, all this discussion in policy, at least in the EU, and for those which are not in the EU, I think also all the regions are considering this. We could see Canada and the US actually having this type of discussions, public discussions, but also going at different levels of looking at software. And one of them was architecture, for example. These practices in software architecture, they have something that's called a tactic. And these tactics are actually architectural decisions for achieving different goals. Just to give you an example, how much concurrency should you have in order to achieve performance goals. And we looked also at architecture, but also at different levels of abstraction, such as automation. And there's plenty of work done and to be done in this area, but I just want to point some results from the trustworthiness sections. So in this EU document, and again, I'm just mentioning this because in our vision is the most mature, it's also closer to us, but I think all the regions are now talking about it. So if you're not from the EU, don't run away. In the EU, the European Commission, which is the main standardization, the main policy body in the EU, they say that for achieving trustworthy AI, you need 7 key requirements, and some of them are coming from the ethical standpoint, such as transparency or privacy or data governance, and some of them are coming from the robustness standpoint, such as what they call technical robustness, but also, the way you prove these things, the way you run risk management, and so on. What's important here is that most of the technical methods, they come from the robustness and a bit of ethical debate. So some of the things that, for example, come from the way we develop robustness against, let's say, adversarial noise, they have straight technical ways of sorting it, while, for societal and environmental well-being, this is a bit of a debate that still has to happen. So based on these 7 key requirements, we restarted the process that we had earlier, and we ended up with 14 new practices that complement the initial 21 practices for engineering we linked them to these 7 key requirements. And just to give you an example of some of these practices, one of them, for example, is testing for social bias in the training data. And you can think about social bias, as in some groups are overly represented or underrepresented, but also as in subgroups. So just to give you an example, if you split your data by continents, for example, you have North America and Europe, and then you test your bias on these continents. Would you have inside these groups, would you have some subgroup bias, such as between males and females, or between people of color, and so on? So some of these practices, we consider them engineering practices, especially the ones coming from testing, because they're very close to the ones that we have for traditional software engineering. And as I said earlier, we restarted the whole process, and we have data again about this practice adoption. And what we saw, and we consider a bit strange, but is the way the world is that actually these trustworthiness practices are the least adopted. And especially the one I talked about, robustness, especially the ones on robustness or on security, they are the least adopted. But of course, as these type of recommendations, they turn into policy, we expect them to grow in adoption.
I think about this quite a bit, actually. Do you feel like that is because it's so new still, and people are trying to just get over the technical parts, and then, like you said, there's a lot of this ethical part that's very hard to define, especially to engineers?
Yes, I think one of the reasons is that there are no direct technical solutions, and also tooling. I think the main facilitator here is the tooling when we talk about engineering. So if you can just import some sort of framework where you have all your tests and you have some tools to interpret the results, that would be very nice. So, but also some of these practices, they don't have direct technical solutions. Right. So when we talk about robustness against adversarial examples, it's very hard to define it and to have a solution. There's been plenty of research on it, but we don't have any solutions.
And I think the EU regulation also talks about like your data set that you're using needs to be fully robust. And that's very hard to say what is a robust data set and what is not. And so there's a lot of gray area in there that I've heard people complain about.
Yes, exactly. So one of the practices that we have that falls more in the governance part is actually trying to have your application audited. So trying to invite other experts to look at it and give their opinions on, how did you tackle bias or some of these concerns that are kind of hard to define. All right. So just one last point, and these are some of the new directions that we're exploring with this survey and with this project. In general, in engineering, it's very interesting to have some sort of maturity model or some sort of capability model to assess the system and try to suggest improvements. So in our case, it's very hard to measure the degree of adoption of these practices, looking, for example, at a repository, as compared to general engineering, where I would say it's a bit easier to, for example, measure some sort of code attributes, complexity, and so on, and define. So what we did here is that we use some methods from psychometrics, in particular item response theory, which basically tries to evaluate and give results to tests that have standard answers, as we had. So, for example, what we came up with is that if you take the survey, then we can evaluate your ML team's engineering ability based on the practice adoption rate. So one of the things that we did is that with this item response theory, we can also deduct the difficulty of adoption per practice and per level. So we have a difficulty of adoption coming from, for example, partial to complete the adoption for each practice. And what you can see in the picture on the right is that we have some interview subjects. In this case, I just selected 3 of them, and then we compare their engineering ability with the overall scores from this item response theory with all the teams in the benchmark. And we can see that, for example, one of them here is they are under the mean, and they're a bit of an outlier even in the data. Some of them are above. But what's important for this is that we can give suggestions for improvements based on the difficulty of adoption and importance of the effects. So here, as I said, we can evaluate the difficulty of moving, for example, from partial to complete adoption, and then we can suggest, as I showed earlier, we can suggest to practitioners if the effort is worth it, and they can do their own trade-offs. Some key takeaways, there's a big demand for robust development. Also, there was a big demand for it before, before machine learning is used. But now with big machine learning, all this discussion is becoming a bit more acute because the impact can be way bigger. And that good engineering practices, in my opinion, at least, there are prerequisites for any quality attributes such as robustness or agility, or thinking more about the system. More about the engineering practices that we see that they're being modified and developed at a very quick pace, which for us, of course, is very nice. But the adoption rate, the rates vary a lot, and the effects are not completely understood yet. We could predict this, but we limited ourselves to 4 effects because many of the effects that are found in the literature, they're not based on technical solutions. And robustness and trustworthiness, they get wide attention by policymakers, but practitioners yet do not adopt these practices. And the reasons, as we talked earlier, we can find a lot of reasons. One of the things that I can tell you is that you can take the survey yourself. You can find it on our website, which is se.ml.github.io. So if you belong to a team of practitioners, you can take the survey yourself. And then here there's the reading list. We have this awesome reading list. We have the catalog of practices that you can find on the website, and you have a lot of other preprints except this paper to read on our website.
So that's pretty awesome. And I encourage everyone to go at least poke around on this GitHub and see what the different practices are, and how I love how you put how difficult it can be to adopt them. And so we can have a realistic version of, oh, cool. Yeah, that seems like something that I want to do. And then you realize that's like super hard, double black diamond to get that adopted. And you realize, oh, maybe I'll try that later, or I can at least be realistic with my scope and how I want to go about it. The question that I wanted to ask you, though, and anyone else that's in here, feel free to throw in the chat, ask any questions. But what I wanted to ask you, Alex, was after you have someone fill out the survey, do you follow up with everybody? Do you follow up with occasional people? How does that look? And then what kind of follow-up questions or interviews do you give?
Yeah, so for us, it would be almost impossible to follow up with everyone, as you can imagine. Talking with 500 practitioners will take a lot of time. But what we do is that we invite people from different organizations, which with different backgrounds and so on, and try to get some sort of a good sample of practitioners. And in the interview, we have the protocol for the interview, and in the protocol, we ask them different questions. For example, we ask them to take the survey first. And after that, we ask them more general about the survey itself, either the questions were clear and so on. And then we jump into, why didn't you adopt the testing practice? Or, what's the context in which you adopted this practice, and which is the most important practice that you find, and so on. Sorry, I think my dog is a bit upset. But
Do you need to go let him in there?
No, I'll do it afterwards.
Okay, nice. Yeah, so I find it fascinating. Are there any best practices that came about that surprised you, that you weren't really expecting?
I won't say so, but I think some of the results that we got from the survey on the adoption rate surprised us, especially that, for example, we would expect that people that use deep learning to adopt less practices, right? Because it's a newer technology, and people that use features for a longer time to have larger adoption of practices. But actually we found the opposite, because using some of these algorithms that do, for example, automatic feature selection, make the process easier for them, right? So as much automation involved makes everything better.
Got some cool questions coming through in the chat. Did you also gather criticism on the practices? For example, I could imagine a practice like assign an owner to every feature is not adopted much because many teams don't feel it is useful and worth the trouble. Now it seems you attribute this to non-adoption. or low skill?
Yes. Yeah. So we actually did find some criticism, but then this is kind of, was balanced by other people that considered this important. So we had the main criticisms were around these trustworthiness practices, because it's very hard to define a solution. In this case, assigning an owner to every feature, some teams consider it very valuable because they have less features, let's say 10 or 15, and they are about personal attributes. And some people that have 150 features consider it completely irrelevant. But because we found this balance, we decided to keep some of these practices in the list. We also had other practices that were completely discarded.
Were there any practices that were discarded that you would have liked to have kept in?
To be honest, to be completely fair, I don't remember right now. But
yeah, there were so many, and you had to figure out which ones. Yeah, that makes
yeah,
sense.
in the end, we also had to find a balance, right? We can have 100 practices that you can adopt, but no one will really look at 100 practices. So we also merged some of them. For example, continuous integration. We had automatic testing and automatically build the building. We had two practices, so we merged them together.
Yeah, it makes sense. Another question coming through, just like cybersecurity, the cybersecurity industry became crowded. Do you think the machine learning industry will become crowded in a few years?
I think it's already a bit crowded, in my opinion. And not, I mean, both in the good sense and in the bad sense, right? So in the good sense, because if there are new problems that we can tackle with this technology, then it would be nice to tackle them. Maybe we have some results. In the bad sense is that the impact of using this technology can be, a bit bigger than with classical software. So if we take high-stake decisions, such as deciding, there's this classical Compass case from the US, where they decide if one of the citizens with recidivate in committing some criminal act, and then the algorithm was very biased and it only selected some groups of people. So in case we use this technology wrong, it's already there. In my opinion, it's already overcrowded. We just have to decide which problems we can tackle easily with machine learning.
Yeah, that's a great answer. Another question coming through, which best practices did you follow yourself when you made the random forest model?
We try to follow most of them, but I think, as you will see in the paper, is that the one that we considered very important is to automate everything, to use AutoML. And this is something that we don't see in other papers that much. And we actually observed some improvements, but then, we ran into some problems of extracting these Shapley values or understanding what the models were doing for us. We used AutoSK learn for it, but the results we got in some cases better results, but we could not interpret them.
And is there a best practice that you felt like is on the hard end of the spectrum, but it is like a necessary? Like if we were to draw the graph, right, where it's like difficult but very important, and where does it land? What are some of those?
I think if we think about production level systems, it's definitely automated testing, regression testing, and automated testing. And this has been around for a while, right? 30 years maybe we do regression testing, but still I do believe is the most important one. And I'm not talking only about unit tests. I'm also talking about automating tests for bias, tests for splitting your data in such a way that you can embed it in the pipeline and run these automatic tests and so on.
That's so funny. You're the second person this week on the MLOps community. The person we interviewed for the podcast was also a huge advocate of testing and how important it is to make sure that you're testing and you don't let anything out the door without testing it, because it can just cause you a world of hurt. So another question coming through in the chat is, what is one single interpretability method you would suggest for GNNs? It's hard to understand them.
So I'm not an expert on interpretability, so maybe I'm not the right person to ask in this case, but I think, yes, I cannot say which is the one single interpretability model. I'm sorry. I don't use graph neural networks either, so my research is mostly on computer vision.
Don't worry about it. It's all good. So the last question that I have for you, and then if anyone else has any more, throw them in. Otherwise, we'll let you go. I'm wondering about how you feel the impact of this paper and the software engineering, like best practices, does it help? Like, how do you get that out there for more people to read it, right? Besides just sending out a paper. And what kind of change are you trying to effect with this?
So what we try to do is to actually, all the research that we do in engineering, we try to make it easily accessible to practitioners. Not so much, well, to researchers, it is accessible through the paper, but what we try to do is, develop the website in such a way that people can access it quickly, find information quickly, understand rapidly where they are with the team, with all the adoption rates and so on, and, try to move from there. So some of the things that we do right now, we try to develop some sort of assessment tools that are some of these that give you instant feedback. So for example, when you select some of the practices, some of the adoption rates, they can give you instant feedback on how to improve, why this is important, and so on. Regarding the research community in general, I think publishing at a good conference for this community is enough.
Getting it out there to everyone by making sure, by coming on the MLOps community meetup. That's one thing. That is one reason why I wanted you to come on here, just to at least share this with us and make sure that a larger audience sees it. Because I feel like sometimes research papers can get stuck in research circles. And this one is very, very applicable to the industry, right? And so a lot of us that are working in companies should see these different things. And also, I know that Google has tried to do something like this when it comes to the ML test score, which you've undoubtedly read. Did you look at any of that when you were creating the
Yeah, so it's one of the
questionnaire?
papers that actually, we cite as related work, and it's, one of them that is doing more or less the same, but in a bit of a different angle with testing.
Yeah. So is the goal now to continue to ask practitioners out there to fill this out and then share your learnings each year as you have them?
This is one of them. This is one of the goals. Of course, we have these automated scripts already, where we can, we can create these reports and share these outcomes yearly and see some of the trends. One of the other things that we're pushing for is to actually form some sort of community that can also contribute to the reading list, contribute more to the open source materials that they can find online, such that we create some momentum, around engineering machine learning solutions. Some of the other things that we do is, for example, I mentioned here, I mentioned here, right? We try to provide practitioners with some sort of assessment tools, and these assessment tools should not be only based for us on new practitioners taking the survey, but maybe, have some sort of continuous integration pipeline where we can automatically check some of these practices or some other practices. So, what's important for us is, in the end, suggest improvements, right? So if you can have some sort of tool that can give you also maybe part of the solution, not only saying that you should, just move from partially to completely, then that's a bit hard to comprehend. I actually do have a Twitter handle. You can search for Alex Serban. So I'll put it here later.
Oh, there we go. Yeah,
it's
cool.
That's stochastic with CH.
And you are in the MLOps community chat as of 10 minutes from now. So if anyone wants to hang out with him and chat with him more, you can find him in the community chat. And that's about it. Alex, this was awesome, man. I really appreciate you on here talking about this. It's super, super interesting stuff for me. I'm going to send this talk to so many people I know, and I know we'll probably spark some conversations in the chat about it. If anyone has anything that they want to talk with Alex about, or just throw it in the community chat, that's the team that you see on the screen that he also works with. So much appreciation to you and the whole team. It's really cool what you all are doing.
Thank you, man. Thanks for the invitation. Of course, it was a pleasure to be here.
All right, y'all. We'll see you next week. Another MLOps community meetup. Success under the belt.